Welcome to another Intermediate Algebra video. In this video, we will begin looking at radicals. All right, so our objectives in this video, we'll find square roots, we'll approximate roots, we'll find cube roots, and we'll find the nth root of a to the n, more specifically looking something like this, where a is representing a real number. The notes for this section. You may have a memory of working with square roots and radicals in the past, and you might be remembering that I, the imaginary number, comes into play at some point, and it will throughout this unit. But in this first video, this is just our introduction, so we're not dealing with the imaginary solutions yet. We only want real solutions in this section, and that will carry through until we actually discuss imaginary solutions. Okay, then the notes that kind of go along with each of those objectives. So A, in all of these three cases, represents a non-negative number or variables. So it could be that we have numbers, it could be a variable, it could be a mixture of the two. And so these are the rules for a square root, cube root, and nth root. And that's how I'll refer to them. We have a square root. Oof, let's fix that. A cube root, and this is called an nth root. And the note is pretty much the same for all of them. If you have something squared underneath a square root undoes that second power. So essentially, the second power and the square undo each other and leave you with a. The same thing happens for a cube root. A cube root, instead of looking for something squared, which a squared means a times a, instead of looking for something squared in a cube root, we would need a group of 3. So we would be looking for something cubed. A cubed is a times a, group of 3. So a single a comes out. So just as the second power and the square root undo each other, the cube root and the cube undo each other. And the same for an nth root. This just means for any exponent and any root, if we have a to the 10th power under a 10th root, they cancel each other out and we're left with just a. So whatever number you see here, whatever value you see in this position, which is referred to as the index, that tells you what type of number or value variables you're looking for underneath. You're looking for groups of 3 in a cube root. You're looking for groups of 5 in a fifth root. In a square root, the index is an implied 2. You don't ever see the 2 written there. It's implied. If the index does not sit there, you don't see a number, it's a 2. All right, so let's see some of these problems in action. We'll get through quite a few in the video, and that's because they're all pretty quick. And for a handful of them, I'm going to show you a few different methods. So the first one, simplify, and the little caveat note that you'll see for almost every problem we do in this video and for a lot of the problems throughout this unit is that all variables are representing non-negatives. It has to be there. If you're curious what answers would look like if that caveat wasn't in place, you can email me and ask about it. But this class is just about kind of the introduction and being able to do the standard computations. All right, so the first question is the square root of 64. Some of you might know that one off the top of your head. It's 8. If you did, fantastic. If not, that's fine. I'm going to show you a different way to get there. The square root of 64 is a perfect square. So if you have your calculator nearby, you can type that in on the calculator. You'll use your calculator, but only in a small way. So I'll give you the description on where to find it. This only works if it's a perfect square and when we do the second objective of approximating. So on the left-hand side on your calculator, if you have the TI-83 or 84, but the 5th button down, you see the square root, which looks something like this. Mine is in blue, so I have to hit the second key before I can get into that. Then it opens up a parentheses. This is what I see on the calculator, allowing me to type in something. If I type in 64 and then close that parentheses, hit enter, I get my answer of 8. You can check answers here, and like I said, this will work for perfect squares, but for where we're going with these things, it's not always going to be the most helpful. So you could use the calculator there, sure. We get 8. If you wanted to use the rule here, I'll call that method 1 in this video. The rule showed something squared being undone by the square root. So instead of writing 64, we could write 64 as 8 squared. And then you'll see, just like the note shows, that the squared and the square root undo each other, leaving you with 8. One way, another way to get to 8. Another way that can be helpful, and to be honest, if it was me doing the work, I would bounce back and forth between the different methods. So I'd suggest you become familiar with all of them. This other method would be to take 64 and break it down to its prime numbers. So we can break 64 down to 8 times 8, each 8 down to 4 times 2, and then each 4 to 2 times 2. So 64 can break down 2 times 2 times 2, 6 times. And then instead of using method 1, where we look specifically for something squared, we look for groups of 2. We look for pairs because we have a square root. We have a pair of 2s, a pair of 2s, and a pair of 2s. For each pair, a single 2 comes out and gets multiplied together, giving the same answer that we got in our other methods, giving us 8. There'll be a time and a place for this method. So I know right now it seems cumbersome and pointless when you can type it in the calculator. Maybe you just know it, but when we get to numbers that we don't just know, we'll need a different method. So 8 is our square root of 64. Okay, the second one, square root of 100. You may know this one off the top of your head. If you do, fantastic. If not, we'll get there. Square root of 100 is 10. If we use method 1 for this, and this one is a perfect square, so you could use the calculator, we would write 100 as 10 squared so that the second power and the square root can undo each other, leaving us with 10. Or we can use method 2, where we take 100 and break it down. 2 times 50, 2 times 25, 5 times 5. So for method 2, instead of 100, we would write the prime numbers that it broke down to. And if your first thought wasn't to go with 2 and 50, but to go with 2 and 10, that's fine. You will always get to the same final list of prime numbers no matter what. 2 times 2 times 5 times 5. And we're looking for pairs. We have a pair of 2s, so a 2 comes out, and a pair of 5s, so a 5 comes out. Everything underneath the radical has been used, so no piece of the radical is left. Multiply those together, and we get 10. Same answer. Okay, the next one is a fraction underneath the radical. You'll see a tiny bit of fractions throughout this unit, very minimal amount. And if you do see them, there's a good chance they're pretty easy to work with or that you're doing some rationalizing. So this one, we're looking for a square root of 4 over 49. And you can think of them independently as 4 and 49. Is there something squared that would give us 4? Something times itself to give us 4? The answer is yes, it's 2. And for 49, again, the answer is yes, it's 7. You can use the two methods if you want to. Method 1 uses the definition. That's why I'm writing it. Practically, it's probably not one that you would stick with. Or you could write using method 2 as 4 as 2 times 2 and 49 as 7 times 7. They're each a pair, so a 2 comes out and a 7 comes out, giving you 2 over 7. Same answer. Okay, the next one. Negative square root of 9. It's tempting to say that if a negative's involved, no solution. If you've worked with radicals before, that might be your inclination. But the negative is only a problem if it's inside. So for example, if we had the square root of negative 9, if we're looking for a number to multiply by itself to get negative 9, it's not going to happen. And here's why. If we were to take two positive numbers, positive times positive, we get a positive number. If I took two negatives, negative times negative, I get a positive number. So this number underneath the radical can't be negative. It can't be negative if we have a square root. So if you have a negative underneath, for the time being, your answer is no solution. But if that negative's already on the outside, maybe this thing is just being subtracted long term. Negative on the outside is fine. You evaluate independently. So the negative is part of the answer. How about the square root of 9? Well, that's a perfect square. Type it in the calculator. Look for pairs. 9 breaks down to 3 times 3. The square root of 9 is 3. And the negative that's in front just comes down as part of the answer. So I don't want you to think that it's not possible to have a negative as an answer here. That negative just won't come from inside the radical. All right, so these were just number examples. Let's take a look at some that involve variables. So the directions simplify. Again, the caveat, all variables are non-negative, represent all non-negatives. So our first one, square root of 100x to the 4th. So, evaluate numbers and variables separately. We've already looked at the square root of 100 on the last slide. We know that that's 10. The last thing we have to deal with is the square root of x squared. If written out, it would look like this. X times x times x times x. 4 of them. If we have a square root, then we're looking for pairs. So, how many pairs of x's do you see? Here's one pair. Here's another pair. There are 2 pairs, so 2 x's come out, and there's our answer, 10x squared. Okay, next one, square root of 81x squared y to the 6th. First, we have 81 to deal with. Maybe you know 81 off the top of your head. If not, I'm going to break down to its primes. We have a pair of 3's and a pair of 3's, meaning a 3 times a 3 comes out. There's no numbers left inside. In this section, they'll all be perfect squares. As we continue on, they won't necessarily be perfect squares. Then we have 2 x's underneath. How many pairs are there if we have 2 x's? A single pair comes out. And then we have 6 y's, 6 of them. How many pairs? 1, 2, 3. So 3 y's come out. Everything was utilized under the radical, so nothing else remains. All that's left is to multiply those numbers and pull it all together. 9x y to the 3rd. You might see a pattern with the variables, and that pattern is that each exponent just gets cut in half, and that's true. If you're taking something and breaking it into groups of 2, that's what divided by 2 means, so you're exactly right. The number part you have to deal with a little bit differently. Perfect square, sure, evaluate it right away. If it's not a perfect square, you'll have to do a little bit more work, but that'll come later. If it is a perfect square like 81, I don't need to see 3 times 3. I don't need to see this full breakdown. I would just be looking for the final answer there. If it's a perfect square, there's no work to show. If it's not, then I'm going to need to see some. All right. Okay, so that completes the first objective, evaluating or finding square roots. Let's look at that second objective, and I only have one problem for it because we so briefly touch on it. If it says approximate, then that means it's a calculator question, and you'll have to be given instructions on where to round. So 52 is not a perfect square. Maybe you know, maybe you don't. It's not a perfect square. But let's get an idea of where that number should fall. So think about what perfect square lies before 52 and after 52. There's a perfect square on each side. On the lower end would be 49, which would give 7, and then above it would be 64, as a square root would give you 8. So right off the bat, you can expect that the numbers should fall somewhere between 7 and 8. You don't have to make that assessment. It's a good practice to go through to give yourself an idea of what your answer should look like. But you'll never be asked to guess what that number should be anywhere between here. So like I said, if it says approximate, it's a calculator question. So you go right back into, on the left-hand side, looks like about the 5th button down for me. Type in the square root with 52, close the parentheses, hit enter, and we get that the square root of 52, now I'm putting is approximately. If you write equals, it's not a huge deal. But you can see it's a decimal that goes on for a long time, and in truth, it's a decimal that goes on forever. So we get 7.211102551, and that's all I see. But this question asks for us to round to 3 decimal places. So I want 1, 2, 3, and then decide if that 4th decimal bumps it up. It's a 1, it does not. So the square root of 52 is approximately 7.211. Like I said, we only very briefly touch on this. It's just to give you an idea that between every perfect square, there is a number that the calculator can find to give you 52 if squared, but it'll never be a nice number if it's not a perfect square. Okay, so that completes the second objective. Let's take a look at the third objective. Third and fourth on this page, as a matter of fact. So the third objective is finding cube roots, which means we're looking for groups of 3. Again, directions are simplify, and the caveat, all variables are non-negative. So for this first problem, we have the cube root of negative 27. Remember, for square root, we discussed it's a problem to have a negative because you'll never multiply 2 things and get a negative. So, is it a problem here? Can we ever multiply 3 things together and get a negative number? If we started with a positive, positive times positive times positive is positive. We won't have negative. If we start with 3 negatives, negative times negative cancels and is positive, times another negative gives us a negative number. So if we have a cube root or any even index number, then we can have a negative inside and still get a value. So that means coming out of here has to be a negative. Okay, what about the 27? We need groups of 3 here. So we have 9 times 3, which is 3 times 3. Since it's a cube root, we need a group of 3, and we have a group of 3. 3 comes out. So it means negative 3 times negative 3 times negative 3 is negative 27. If you keep the negatives when you break it down here, that's fine. You don't have to. You can just evaluate, should the negative come out, should it not, and then the numbers separately. Okay, how about the cube root of, let's go with this one next. The cube root of x to the 21st. If it helps you, you can always draw out the string of, not that. 1, 2, 3, 4, 5, 21 x's. You can always do that and then lump together the groups of 2, 3, whatever your index asks for. Or you can just think through, kind of imagine the string of 21 x's. How many groups of 3 would there be there? 1, 2, 3, 4, 5, 6, 7. Or, like we noticed as a pattern in the previous problems, division. 21 divided by 3 gives us 7. So, x to the 7th comes out. Okay, let's do the other cube root. Cube root of 125, x to the 9th. We're looking for a group of 3, something cubed, to get us 125. So let's break this down and see. 5 times 25 gives us 125. That 25 breaks down to 5 times 5. And then 9 x's. How many groups of 3 would there be? We have 3 groups of 3. So what comes out of here is a 5 and an x to the 3rd. So 5 cubed gives you 125, x cubed, quantity cubed gives you x to the 9th. And then the same idea carries forward to an nth root. So these two are examples of nth root problems. It just means a different number than 2 or 3. Anything else counts as an nth root. So let's start with this 6th root. Is there anything multiplied by itself 6 times that would give you 64? Now it's tempting to see a radical and 64. It's tempting to just say 8 must be the answer, but it's a 6th root, which means you're looking for groups of 6. So if you break down 64, sure, you start with 8 times 8, but that 8 continues to break down. And we have 1, 2, 3, 4, 5, 6 2s. We need a group of 6. 1, 2, 3, 4, 5, 6. So a 2 comes out, and then there are 18 x's. How many groups of 6 are there? 1, 2, 3. Divide, and you get 3. So 2x to the 3rd. Okay, one more with me. Our last nth root problem, we have the 5th root of -1. First of all, decide if the negative's okay. It's on the inside, so we do need to think about it. Can you multiply anything by itself 5 times and get a negative? Really, the question is only around, can that be a negative? So if we have negative, all negative, these 2 would cancel and be positive, these 2 would cancel and be positive, the last one would multiply and give us a negative outcome. So that's definitely possible. How about 1? Is there anything you can multiply by itself 5 times to get 1? This one's a little tricky. The answer is yes, it's 1. 1 times 1 is 1, times 1 is 1, times 1 times 1, and if they're all negative, you'll end up with a -1 at the end. So this one is -1. Make sure you're aware what index you have as you go through the problem. That tells you what size groups you're looking for to be able to pull out of the radical. Okay, so go ahead and practice these problems. The first one is the only one that I want you to use the calculator on. You can see that it's a decimal, and you'll see a tiny bit of decimals here, but really only when your intention is to use the calculator. You don't have to round, it won't require rounding. And then the rest, do by hand. Pause the video, I'll see you in a moment. Okay. All right, so the first question, if you type in the calculator, you may recognize the end piece, the 169, as a perfect square. Maybe not. The square root of just 169 is 13, so it's no surprise that when you type this in the calculator, you get 0.13 or just 0.13. No rhyme or reason on why you should put either one. The second one, let's go with the square root. We're looking for something multiplied by itself to get 121, or groups of 2. 121 only breaks down one way, and it's 11 times 11. So we have 11, and then the variables, there are 8 x's. How many groups of 2? 1, 2, 3, 4. X to the 4th. Then our cube root. First we decide if the negative's okay, and it is because it's a cube root. We can multiply something by itself 3 times and still have a negative, so that comes out. How about groups of 3? If we take 64 and break it down, this is a popular number in this unit. We want groups of 3. We have 1 group of 3 and 2 groups of 3, which means 2 times 2 comes out, or 4. And then 12 x's, groups of 3, we get 4. So negative x to the fourth, negative 4x to the fourth for that cube root. And then the last one is a 6th root. There's no coefficient, all variables. So how many groups of 6 do we have in the 12 x's? The answer is 2. For the y's, we have 24. Groups of 6 is 4. And then from z to the 6th, there's 1 group of 6, so a single z comes out. If you were to type in or write the exponent of 1, that's fine. It doesn't need to be there, but it's not wrong if you do put it there. All right, so that finishes up our intro look at the radicals. I will see you soon for another video where we continue on that journey.